The next speaker, I would like to invite Dr. Chen. Yeah, your spelling and the pronunciation is quite challenging. Yeah. 郑明展, yeah. For most of the people, you probably know him. You met with him because he's like so well known. But if you haven't met with him, you probably also use his database. Yeah, because he established a database for Cancer Center of the Singapore, and that being very popular because the data is a solid, completed to link with the clinical. So that's become very useful. Yeah, Dr. Zhang received his MD from the University of Queensland, Australia, and then follow with that, he received a PhD training from Karolinska Institute of the Sweden, and after that, he returned to the Singapore to serve the National Singapore University Cancer Center. He's now the Deputy Cancer Center Director to the National Cancer Center of the Singapore. And very important is I try to keep him stay a few more days to interact with you all, but he couldn't because he got an award from the president of the Singapore. So congratulations and welcome to give the wisdom talk.
Thank you very much, Professor Yan, for a very kind introduction. Good morning to everybody. First of all, I'd like to thank the organizer for this kind invitation and also for the opportunity to share with you some of the works. The first part, I'm going to talk about kidney cancer. Second part, if I have time, I'll talk to a little bit more sensitive things, which we discovered many years ago, and that is the Matolingson. Anyway, this is our new building. We just moved in 2.5 years ago. This is a National Cancer Center, and rumor has it that it is the most expensive government building in Singapore. Because in the basement, there is a proton therapy that costs 150 million. Anyway, many years ago, when I moved from United States to Singapore, there was the time of second-generation sequencing. So we did a lot of genetic profiling in the Asian prevalent cancers. And to our surprise, at that time, we found a lot of novel mutations in chromatin enzymes. So that triggered my interest to explore the epigenomic impact of these mutations. And so today I'm going to tell you the story of how we engaged the epigenomic approach to study the carcinogenesis, especially in clear cell carcinoma. So, okay, so this is also this work also helps us to understand the crosstalk between genomics and epigenomics in cancer. Okay, so the model cancer that we want to focus on is the clear cell renal cell carcinoma, which is the most common type of kidney cancer. And when we talk about clear cell kidney cancer, we always think about von Hippel-Lindau disease. So on the left is the German ophthalmologist, Dr. von Hippel, and on the right is the Dr. Arvid Lindau, the Swedish pathologist. So they first described the syndrome, hereditary cancer syndrome that's named after them, and that's a VHL disease, 1 in 30,000. And then characterized by retinal angioma, cerebellar hemangioblastoma, clear cell renal cell carcinoma, pheochromocytoma, and pancreatic islet cell tumors. So, but for a long time, many decades, people already know that clear cell RCC always harbor the loss of chromosome 3p. And I think some of you know that this nuisance, can't move. Okay, nuisance two-hit model. This is a model that is indicative of the presence of tumor suppressor gene. So what our nuisance proposed at the time, oops. what Al-Nussan proposed is that in the hereditary cancer syndrome such as VHL, the patients are born with a one mutation. And then the wild type copy was lost sometime later in life. And of course, this suggests that the VHL gene must be located in chromosome 3p because there's always the loss of chromosome 3p. In the sporadic counterparts, both the mutation and the wild type copies are lost or mutated much later in life in the affected tissue. So sure enough, the gene for VHL was mapped to chromosome 3p and subsequently identified in 1993 through positional cloning. And of course, many years of hard work to study the function of VHL, 有比较好的 Anyway, the functional studies of VHL finally contribute to the 2019 Nobel Prize for Physiology of Medicine, Bill Kaelin, Peter Radcliffe, and Greg Semenza. So what it shows is that the VHL gene is the recognizing unit of the E3 ligase. So in the presence of oxygen, these ubiquitinase will recognize the HIF hypoxia-inducible factor, the transcription factor that has gone through proteal hydroxylation. And this leads to the proteasomal degradation of HIF hypoxia-inducible factor. And in the kidney cancer, because which you point to where? Oh, okay, next slide. Next slide. Okay, in the tumor, because there's a loss of VHL, the VHL cannot degrade the HIF. So this is what we call a pseudo-hypoxia situation. Next. So because the degradation of HIF cannot take place, you have accumulation of HIF, and therefore you get the upregulation of HIF target genes, such as IGF-BP3, VGF, GLUT1, etc. Next. And this pathway has led to the discovery and approval of several drugs for kidney cancer, including temsirolimus, bevacizumab, sunitinib, sorafenib, pazopanib, etc. Next. So our question is whether VHL inactivations can change the epigenomic landscape of the clear cell RCC and therefore impact tumorigenesis. Next. So we started by looking at the histomark profiling, including the H3K27 acetylation, H3K4 trimethylation and monomethylation, and that is to look at the activities of the promoter and enhancer. Next. And sure enough, we can see the big difference between the normal tissue and the tumor tissue. You can see gain of promoter, loss of promoters, gain of enhancers, loss of enhancers. Next. But what is interesting is that if you look at the genes that are affected by the gain of promoters, they are all housekeeping genes. But if you look at the genes that are affected by the gain enhancers, they are clear cell RCC specific. That means that such as a HIF alpha network, renal cell carcinoma signature, group 1 transporter process. So these are all very clear cell RCC specific. Next. So, and you restore the VHL, it will lead to the loss of these enhancer entities, suggesting that this enhancer entity is really tumor specific. Next. And then okay, next. So we again showed that this loss of enhancer after VHL restoration is only found in the clear cell RCC, but not in other cancer types. This is very, very clear. Next. So at that time, Rick Young just published a paper in Cell describing super enhancer. This is multiple copies of enhancers suggesting that the gene that is regulated by super enhancer are usually master regulator. There are several of them. Some of them already know, but we identify one that is novel at the time. It's called ZNF395. Next. So when we deplete the ZNF395 gene, you can see that it has very strong inhibition of the tumor growth, both in vitro and in vivo. It's a very, very powerful inhibition when you deplete the ZNF395. Next. And subsequently, we also show that VHL restoration or HIF2 knockdown, it also diminished the ZNF395 super enhancer activity and its gene expression. Next. And furthermore, HIF2 recruits histone acetyltransferase P300 to ZNF395 enhancer, suggesting that the HIF2 regulate ZNF395. Next. So this is, at that time, we published this paper in Cancer Discovery. We showed that the VHL loss activates master regulator, especially ZNF395 of clear cell RCC through the enhancer activation. Next. The question now is, what is the function role of ZNF395? Next. So, VHL loss results in significant metabolic rewiring and mitochondrial burden. Next. Next. So in the normal cells, you know that the glycolysis will go through the TCA cycles and then go through the electron transport generating energy. But in tumor, we all know about the Warburg effects. So the acetyl-CoA were diverted to the lactate. So there will be a less carbon flux through the TCAA cycle. So you need to replenish the TCA intermediate accessor, and this is through the glutamine-dependent reductive carboxylation, which is the glutamine shunt or glutaminolysis. So the question is, next. We know that this glutamine shunt is not that regulated by HIF2. So the question is, what actually regulate, or what master regulator regulate this glutamine shunt and the reductive carboxylation? Next. So ZNF395, we found out that it is highly specific for clear cell RCC. As you can see, this is a TCGA data. So many cancer types, but it's only highly expressed in clear cell RCC, as you can see here. And single cell studies also show that it's only expressed in the tumor cells, not in the myeloid or lymphoid tissue. Next. So we then look at ChIP-6, and we show that the ZNF395 occupies the promoter regions of many metabolic enzymes. And you can see that if you look at the gene ontology, almost all processes are metabolism related. Next. So we then showed that one of the two metabolic enzymes, the GLS glutaminase and IDH2 isocitrate dehydrogenase enzyme are highly regulated by ZNF395. Next. And as furthermore, you can see that a lot of these metabolic enzymes are regulated by ZNF395. And I suppose by now you probably can guess that this is the master regulator for the whole glutamine and shunt, which is a very important metabolic process. Next. And again, we show that ZNF395 maintains TCA anaplerosis. It provides all the intermediates in the TCA cycle, because at that time, the carbon was already diverted away from TCA cycles. And when you knock down the ZNF395, you can see that all the TCA intermediates, the amino acids, and even the redox ratio, the redox index were all down-regulated when you deplete the ZNF395. Next. And this is a carbon tracing. And again, you can see that from the glutamine, all this will go through and form the TCA intermediates as well as all the amino acids, related amino acids. Next. And furthermore, we showed that the ZNF395 maintains oxidative respiration. We showed that it maintains a basal maximal aspect respiration process. Next. And even when we replace the complex one, in this case, the yeast mitochondria NADH dehydrogenase, you can actually increase the survival activity, property of the tumor cells when ZNF395 is knocked down. Next. So in summary, we identified the master regulator of for glutamine or glutaminolysis or glutamine shunt. And this is obviously an important part in the cancer biology. And of course, this paper is coming up. Next. So previous slide. So we are currently collaborating with Extopi, AI drug discovery company, to develop a peptide inhibitors for ZNF395. This is quite interesting because we know that very recently, next slide, belzutifan, the HIF2 inhibitor, has been approved for treating VHL disease and kidney cancer. And we are still seeing patients that develop resistance to this new drug. And we believe that ZNF395 may play a role in the resistance of HIF2 inhibitor. This drug, the way it works is that it inhibits the binding of the HIF2 alpha and HIF1 beta. And this is the mechanism, but already patients are developing resistance. Next. Okay, next. So I'm going to tell you a second story about clear cell RCC. So the question is whether VHL inactivation is enough to cause clear cell RCC. We have this question because when we knock out the VHL gene in the mice, next slide, we did not see tumor formation. What we see is a skinnier mice or smaller mice. And you can imagine that's because of HIF role in all the metabolism. So when you have this regulation of metabolism, your mice is smaller, but it does not give you the kidney cancer phenotype. Next. So many years ago, when I was doing my PhD, I actually published a paper in Lancet showing that there is an entity called familial non-VHL clear cell RCC. In this family, I managed to exclude the linkage to VHL. The main message is that there must be other kidney cancer genes other than VHL. And this is 1997. And it took 10 years for me to identify the gene, the non-VHL gene. Next. And this is the gene that we published in Nature together with Sanger Center. And this is the gene called PBRM1. I lost the battery. PBRM1, which is a part of the Schwann nerve complex. Next. Okay. Okay. Anyway, so interestingly, I show you a chromosome 3p, the loss of chromosome 3p, and I told you a story of VHL. 你还有一次吗？他的跑不出来。有吗？不用紧，不用紧，我用手指。So the gene is called PBM1, and 这个不行，不能走。技术问题。有了。Okay. Okay. So it turns out that, and I told you about our Knudsen's two-hit model. I think most of you know our Knudsen, who got a Lasker Award for this tumor suppressors gene. But interestingly, in the clear cell RCC, it's not 2 hits. It's almost 8 hits because there's a gene VHL, and then which is mutated in 50 to 70% of clear cell RCC. The second gene is PBM1, the one we identify. It's mutated in 40 to 50%. The other one is SETD2, which was also identified by us, also in a Nature paper. And then the fourth one is a BAP1. So today I'm going to tell you the function of PBM1. So interestingly, there is a family I told you that have clear cell RCC that doesn't have VHL mutation, and it turns out that they have the germline PBM1 mutation. And Charlie Swanton and others, they showed that through the intratumor heterogeneity studies, they show that both VHL and PBM1 are truncal mutations. So the question now is, what is the function of PBM1? Just now I show you the VHL epigenomic and show that there is a enhancer activation. So now we want to work on the PBM1 mutation and to work out its function. So PBM1 is an accessory subunit of the Swiss nerve complex. This complex is highly mutated. I think it is mutated in 20% of all cancer and only second to P53. And if you look at the structure here, this PBM1, and pay notice to BRD7, which is a neighboring subunit. And what basically we show is that, of course, we know that the Swiss nerve complex is a chromatin remodeler, and basically it can change the structure of the complex to facilitate gene regulation. And what happened is that, first of all, we show that it has a tumor suppressor property. When you knock out PBM1, you basically increase the tumor growth, and if you restore the PBM1, it suppresses the tumor growth. And what happened is that when you knock out the PBM1 or you lose the PBM1, whether it's through inactivating mutation or loss of the wild copy, you also lose the BRD7. So structurally, both the PBM1 and BRD7 are lost. And in that case, you have a new structure of Swiss nerve complex. And we know that in the normal wild type Schwann nerve complex, it usually binds to the promoters. But once you lose the PBR1 and BRD7, the structure change and it binds to the enhancer instead. And this is, I think, our key finding, our short. Basically, the new complex without the PBR1 and the BRD7, they bind to novel sites, the de novo peaks. And the question is, what genes are located in these de novo sites? And so these de novo sites, just to cut the story short, we show that it basically involves NF-kappa B. So in the wild type, they don't bind to NF-kappa B, but when you have a mutated PBR1 with a subsequent loss of BRD7, the structure of the complex change and they bind to NF-kappa B. So kidney cancer has been known to have a very strong immunogenic property, and this could be one of the reasons why kidney is immunogenic, and because of the upregulation of NF-kappa B through this mechanism. So anyway, we know that NF-kappa B play a very important role, including inflammatory and immunology. And this is a canonical NF-kappa B that is involved in the PBR1 deficient tumors. And we show that the members of NF-kappa B are upregulated in the PBR1 deficient tumors. And basically what we show is that in the tumors that have a PBR1 deficiency, you can try to use a proteasome inhibitors, and indeed it reverses expression here. And you have a high expression of the NF-kappa B, and if you use a proteasome inhibitor, it does inhibit NF-kappa B related genes. And this is proven in both in vitro, as well as in vivo. So again, now we have a target, therapeutic target, and also a potential drug. But of course, we have to do clinical trials and to prove that. And when you look at the TCGA data, if you look at the two groups, the PBR1 deficient versus PBR1 proficient, you can see that the PBR1 deficient tumors have high expression of the NF-kappa B related genes. So this is basically the summary. The whole Schwann nerve complex structure change when the PBR1 is lost, and when the neighboring BRD7 subunit is also lost, and the new structure or the new complex will bind to a new site, regulate a different set of genes. And this model is now shown in another tumor called clear cell sarcoma of kidney. We haven't published it. This one involved the B called ITD, but the concept is the same. Basically, some of these key biological complexes, they change their structure once they have a mutation, and then they bind and regulate a different set of genes. Okay, these are published in Nature Cell Biology a couple of years ago. I'd like to thank the very talented postdoc Xiao Sai and Jing Han who did most of the work. So I thought a few minutes I want to share with you unpublished data. Some of you may know that many years ago we published these two papers that somewhat created a lot of discussion or controversy, and even heated discussion, especially in China. I was told that one paper has 1 million comments in the social media within 1 week. This is, we started by studying this urothelial cancer with Changkong Memorial Hospital. At that time, I was just curious. We want to know what mutations cause the cause this tumor because it's very rare in the West, but rather common in Taiwan. And of course, it's related to aristolochic acid or matolin. And the metabolite of the aristolochic is the one that binds to the DNA and subsequently lead to the mutations. And this plant has been used in the traditional Chinese medicine preparation, particularly for slimming, arthritis, etc. So at that time, this is more than 10 years ago, we showed that this tumor harbor probably the largest number of mutations because we did a very interesting comparison. We looked at the ultraviolet light related melanoma, and this is whole genome, and we found 260,000 mutations. But when we look at the AA, which is aristolochic, related tumor, the UTUC, it has 460,000 mutations. So we can say that this is the king of kings in mutation. And what is also even more interesting is that it gives you a pathognomonic, very unique mutation signature. And there is always A to T, T to A transversion. You can see all the A to T, T to A transversion. Obviously, this is an important issue and also related to public health. And then we did a very important experiment. We exposed the AA to the normal kidney cell line, and after 6 months, you see this unique A to T tissue signature. So this is from wild type, and after 6 months exposure to AA. So at that time, Sanger Center published they described 21 different mutation signature, but they did not have the AA signature. So our AA signature has since been labeled as number 22. So if you come across mutation signature 22, that's an AA signature. Very recently, only this year, they described 22B signature. And that signature comes from Eastern Europe, Romania. So our Taiwan signature is 22A. The 22B come from Eastern Europe. Okay, so as I said, these two papers attract a lot of attention. The first paper came with a 4-page article from Caijing, which is a top business journal in China. They describe and mention my name and say that how this paper affect the stock market of the listed TCM company. The second paper, when we associate, because I thought that if this carcinogen affect the kidney, the other organ is probably liver. And sure enough, we found a lot of mutation signature in the liver cancer. And this time, it created a bigger storm in China. And this is the statement from China FDA addressing our paper. Now, the problem is that with this paper in liver cancer, a lot of people in China say that the patients also have hepatitis B or C. How do you know that it's not because of hepatitis? This matolin AA could be just bystander effect. So this is next unpublished data. I'm a bit concerned to publish this. So working with Truncal again, we selected 105 cases which are hepatitis negative, non-B, non-C. And we did all the whole genome and show that there is no integration of hepatitis genome. And you see the percentage, how many have the AA signature? 80%. So yes, I still not sure it should publish on. I'll get a lot of phone calls from the TCM. Every time we publish paper, there will be phone calls to hospital from certain society. Anyway, but I think You know, and this time it's very interesting. It's very important because the mutation are P53, and this P53 mutation, most of them are A to T, T to A. Clearly show that is the AA's nature. To me, is that we all say that the AA is banned, but how come it's still there? I just wonder whether there are other things that we don't know or other plants that we don't know that may have a similar component. And hopefully that with some of you, we can do a more collaborative study. I know in the past when I mentioned, but most people don't want to work on this thing. But I think it's quite, we did another analysis. This is a very allele frequency. So it is an indicator to gauge the time and sequence of mutation, how early the mutations take place in this tumor. And interestingly, we showed that they are predominantly early events. It's not that they come from later after the patient get cancer, then they eat some of these herbal plants. So it started very early. And so the mutation, the P53A mutation, when we look at it, they are likely to be early driver event. So with that, this, as I said, unpublished, I want to stop here, and I want to thank Xie Yong, and then from Truncal Memorial Hospital. Thank you so much.
Thank you, Dr. Chen, for the wonderful talk. So now we open to the floor. Yeah, Xinjian, please.
Yeah, Minzhan, very interesting and very exciting. All three stories, very nice. My question to you is about the HIF2.
Okay, yeah.
About the so I assume that the ZNF395 only associates with HIF2 rather than HIF1.
Yes, but HIF1 can also regulate some of the genes, but not HIF, definitely not HIF2. They have nothing to do with it. So we think that in the HIF1 now tumors, some of them don't have HIF1, it will be even more sensitive to ZNF395 depletion. Yeah.
So in this case, the HIF2 actually serves more like a coactivator because it brings this P300. So if you analyze the motif of activated
CSL,
you will find it's more ZNF395 rather than HIF.
Yeah.
Rather than okay.
Yeah. So HIF2 regulate the ZNF395 through the enhancer, the super enhancer. It brings in the P300. But the ZNF395 regulate all the metabolism genes by binding to the promoters. Yeah.
Right. So it's more about, so one more follow-up. So didn't you say that this zinc finger protein is the expression is rather specific to the renal carcinoma?
Yes.
Why is that?
So because of hypoxia. So most of the tumors, if you look at them, there's no high expression of ZNF395. The exception is in the kidney cancer with the VHL now, because there is a HIF2 regulate them. The other situation is if you put the tumor in the hypoxia chamber, then you will see the ZNF395. So the key is so ZNF395 basically is a hypoxia responsive transcription factor that regulate the glutamine. Yeah, because HIF2 doesn't regulate the glutamine at all. Yeah.
Okay, thank you.
So it's hypoxia.
Yeah.
Yeah, Dr. Wu.
Thank you very much for your excellent presentation. I think that the evidence between madorinsuan and RCC and NAMI-NAMC HCC is strong and convincing, but it's low on HBV or HCV related hepatocellular carcinoma may need longitudinal follow-up because for advanced cancer patients, they tended to take any medicine that give them hope. So I think for HBV and HCV related HCC, the role of madonistan may need longitudinal probe to prove the cause effect.
I think some tumors are like that, but some tumor we analyze, we see that the mutation from the madonistan appear very early. But these days you can use a bioinformatic analysis to show that. Probably two groups of a tumor.
Very good point.
Yeah, but very good point. Thanks.
Yeah. Yep. Dr. Chan. Yeah. No. Yeah. Guang Yu.
Thank you. So thank you for your talk. And I know that for AA studies, you're very famous in this field, including HCC and UC. And also I would like to acknowledge the RCC, right? So for RCC, I also have a question. Since AA signature, some of RCC shows AA signature, particularly in Taiwan. Does this have a different genomic characteristics comparing to the RCC in the other area of the world?
Yeah, so the other area, the other country that has the same thing is Romania. So I don't know if you know the Balkan nephropathy. So usually some of these patients always have that kidney failure. From what I understand is that in Romania, they grow the wheat, but they also have the Aristolochia plants in it. Apparently, from what they told me is that when they make the bread from the wheat, they include the plant because apparently it enhances the taste. That's why the other country that have this problem is in Romania, the Eastern Europe. In fact, that one kidney has been published, but they haven't published liver cancer yet. We are looking at that. But there is a slight difference. If you look at the signature, the Taiwan's AA signature A to T is 1 peak. The one that from Romania is 2 peak. That's why now they divide them into A and B, 22. Yeah. But we are trying to study also the Romania cases. Yeah.
Yeah, Dr. Zhang.
Congratulations.
Thank you.
And also your ZNF, the peptide inhibitor, because the potential, including the HIF2 in addition to the resistance, but also it induced a lot of side effects, especially the bone marrow and the hematology, the suppression. And then what do you think about that? Use the ZNF, the peptide inhibitor, what's the potential?
Because
those benefit or the drawback.
Yes. The HIF2, as you know, it regulates so many other things. So when you inhibit, you expect probably more side effects as well, like the glycolysis and all this. But maybe with the ZNF 395, it's only for the glutamine shunt, probably less. I mean, it's just speculative. We're hoping to do more study now because knowing that there are more and more patients develop resistance to the HIF2 inhibitors.
Yeah, because the time is limited, I'm going to hold up with here. Yeah, if you have a further question, you can use the break time to ask the beam. Thank you.
Thank you, Baba.